You know, breakthroughs in clean energy don't always happen in some massive billion-dollar lab. Sometimes they come from the super focused work of just one person. Today, we're going to dive into a PhD thesis that takes on a huge problem in fuel cell technology, and we'll see how this one project could seriously help shape the future of clean power.
It really all boils down to this one simple but absolutely massive question. I mean, we all want clean, green energy, right? But for it to be a real-world solution for everyone, it has to be affordable and it has to be dependable. Well, this research goes right after that challenge by completely rethinking the heart of a fuel cell.
Okay, so here's the deal. The most common type of fuel cell out there, a solid oxide fuel cell, has one major drawback. For it to work, it has to be crazy hot. We're talking nearly 1,000 degrees Celsius, and that extreme heat just creates this whole cascade of engineering nightmares. So why is this heat such a villain for fuel cells? Well, it's not just about the temperature itself. It's about the domino effect it has on everything: the cost, how fast it works, and how long it lasts.
Think about it. At 1,000 degrees, you can't just use regular metal parts. No way. You need these specialized, really expensive ceramics that can handle that kind of punishment. Plus, the whole system takes forever to heat up, which is not great when you need power right away. And all that intense heating and cooling causes stress, it causes cracking, and ultimately it means a shorter life. So the goal is clear. Find a way to get the same awesome performance, but at a much cooler, more manageable temperature. And that brings us to the hero of our story, a special ceramic material called gadolinium-doped ceria, or GDC for short. Scientists had a hunch that this could be the key to building a lower temperature fuel cell.
Now, to really get why GDC is so special, we need a quick refresher on what an electrolyte does. It's basically the gatekeeper in the fuel cell. It blocks electrons on one side, but it lets charged oxygen atoms, the ions, pass right through. This movement of ions is literally what generates the electrical current. So the better the ions can move, the more efficient the fuel cell is. Simple as that.
And this is where GDC really shines. Its unique crystal structure basically creates these bigger, wider channels for those oxygen ions to just zip right through. And what that means is it has fantastic ionic conductivity even at what we call intermediate temperatures, say between 500 and 700 degrees Celsius. That's a huge drop, and it could potentially solve all those heat problems we just talked about.
But, you know, having a promising material is one thing. Actually making it perfectly is a whole other challenge. So the first big hurdle in this PhD research was to create an optimized GDC in its solid, or bulk form, to find the absolute best formula. This process is called the ceramic route, and it's actually a lot like making high-end pottery. You mix your raw powders, you do an initial bake to form the compound, you press it into a shape, and then you fire it in a kiln at incredibly high temperatures. This final step, called sintering, is absolutely crucial. It fuses all the little particles together, gets rid of any tiny holes, and creates a dense, strong final product. Okay, but how can you actually tell if all that baking and firing is really improving the material? You've got to look inside, deep down at its crystal structure. And this right here is how you see success at the atomic level. What you're looking at is X-ray data, and it acts like a fingerprint for the material's internal structure. Now look at the graphs on the left. Before that final firing, the peaks are broad, kind of messy. That tells you things are disordered. But now look to the right. After firing, bam! Those peaks are super sharp and defined. That is the aha moment. It's proof that the atoms have all snapped into a perfect crystal lattice, creating an absolute superhighway for those ions to travel on.
That firing process also completely remodels the material's internal landscape. It causes these tiny crystal grains to grow and merge together. You can see it right here in this chart. The hotter you fire it, the bigger the grains get. Think of it like paving a road. Big, smooth paving stones are way better than a bumpy cobblestone path, right? Larger grains mean fewer roadblocks for the oxygen ions, which smooths out their journey and boosts performance.
And all of this work leads to the big payoff. After all that optimization, the research achieved a peak conductivity of 0.121 Siemens per centimeter. And here's why that's so brilliant. This value is hit at only 800 degrees. That nearly matches the performance of conventional materials that have to run 200 degrees hotter. That is a huge step forward. So, the bulk material was a huge success, but to really push the limits and get that temperature down even further, the researcher had to think smaller, way smaller. The next logical step was to go from a solid pellet to an ultra-thin film. To do this, a much more advanced method was needed: spray pyrolysis. Okay, imagine a very precise, very hot spray painting process. You take a chemical solution with all the ingredients for GDC and you spray it onto a heated surface. The tiny droplets instantly react and deposit a solid, ultra-thin layer of perfect GDC right where you want it.
And the results were just incredible. Using this technique, the researchers successfully made a dense, super high-quality GDC film that was just 13 micrometers thick.
To put that in perspective for you, a single human hair is about 70 micrometers thick. This new electrolyte layer was more than 5 times thinner than that. This is a total game changer because a thinner electrolyte means way less resistance and even better performance at even lower temperatures. All right, now for the final test. A perfect film is great, but does it actually work in a real device? The final step was to build a half cell. You can think of this as the core engine of the fuel cell. The researcher took that brand new ultra-thin GDC electrolyte and deposited it directly onto an anode. That's the part where the fuel reacts. This is the ultimate proof of concept. And this table right here, this just summarizes the triumph of the whole project. The half cell was perfectly thin, it was over 96% dense, which means it's gas-tight and safe, but the real headline is that bottom line. It achieved the target conductivity at just 500 degrees Celsius. That's a 300-degree drop from the optimized bulk material and a whopping 500-degree drop from conventional fuel cells. Just a massive, massive leap in efficiency. So why does one PhD thesis matter in the grand scheme of things? Well, because it provides a detailed, proven roadmap for building a key component of a next-generation fuel cell. Let's just quickly recap this whole journey. It went from perfecting the bulk recipe to pioneering a new thin film technique, and finally, to building a real functional half cell that performs at dramatically lower temperatures. Every single step was a critical achievement that built on the last one to solve that core problem. And look, this isn't just some academic exercise. The researcher says it directly in the thesis. The goal was always crystal clear: to help bring cheaper, more reliable fuel cells to the market. This work provides a practical foundation to actually make that happen.
You know, you can think of it this way. This PhD thesis has essentially perfected the engine of a new kind of fuel cell. The foundation is solid. So the question it leaves us with isn't if, but when. When will we see the other parts of the fuel cell catch up to this breakthrough so we can finally assemble and commercialize these cheaper, more durable, and more efficient fuel cells for a cleaner energy future?